ahead and work one more titration problem while we're on the topic of titration, and hopefully we can understand what's going on a little bit better. Okay, so let's calculate a titration of a weak acid with a strong base. Okay, so this is a weak acid, strong base titration. Okay, so for our example, we're going to be reacting HF, which is a weak acid, with potassium hydroxide. So our overall reaction is HF plus KOH goes to KF plus H2O. Okay, so we're going to be starting with 150 milliliters of 0.10 molar HF, and we're going to titrate that with 0.050 molar KOH. So remember, this means that we have 150 milliliters of HF in our Erlenmeyer flask, right? And that's 0.10 molar HF. And then we've got a burette set up above it, right? And we're going to be adding KOH a little bit at a time, and that KOH is 0.050 molar. So let's calculate the pH in different regions of our titration graph, okay? Let's calculate the pH. A at 0.00 milliliters of KOH, okay? B at, and we can assume that we have enough sig figs here, so let's say 150.00 milliliters there. 35 milliliters of KOH, okay? So at the beginning of our titration, before we add any KOH, after adding 35 milliliters of KOH, after 150 milliliters of KOH, and D after 300 milliliters of KOH. All right, and the Ka for HF, right? The Ka for HF is equal to 6.6 times 10 to the minus fourth. Okay, so let's consider our graph here. All right, so remember, this is a weak acid with a strong base. So we're going to be graphing pH from, say, 0 to 14. Let's just make a line here at 7. That would be neutral. We're going to calculate pH. We're going to plot pH versus volume of KOH. And we can expect the graph to look something like this. So let's go ahead and draw what we expect our graph to look like. So we're going to start with a low pH. We're going to find the equivalence point and go to a high pH. So at some point, we're going to reach the equivalence point, right? And that equivalence point is going to be slightly basic because at the equivalence point, we've used up all of our acid and all of our base. So at the equivalence point, our pH is governed by the concentration of fluoride ion. And this is a weak base. And so we can expect our pH to be slightly basic at the equivalence point, right? At 0 KOH, we can expect to be acidic. So this is going to be in a low pH range. As we begin to add potassium hydroxide, our pH begins to increase, okay? So as we move along this graph, our pH begins to increase. And so at some point, we'll have a slight increase. Maybe at our 35 milliliter mark, we can expect to have a slight increase in pH. Now, what is governing the pH calculation right here? This region where we're going from a small amount of base, where we have some base, to the point, to the equivalence point, okay, then we have some base and its conjugate. So we have some acid and its conjugate base, right? We have some acid and its conjugate base. So notice that the potassium hydroxide is a strong base. It's going to completely deprotonate the HF 1-to-1. So for every mole of potassium hydroxide we add, we're going to form 1 mole of potassium fluoride. So we're going to get 1 mole of fluoride ion. So in this region, we have basically Kf, right, which is our fluoride ion, which is a weak base, and we have HF mixed together. So this is our buffer range. This is the buffer range right here. In this range, we have a buffer. And so in that range, before we get to the equivalence point, but after we start adding base, we can calculate the pH with the Henderson-Hasselbalch equation. All right, so at the equivalence point, when we have no moles of acid and no moles of potassium hydroxide left because they're exactly reacted with each other and everything has been converted to product, we have only the fluoride ion governing the pH, and therefore our pH will be governed by the concentration of the fluoride ion. Okay, and so as we move into this region here, this is our basic region, and our pH is going to be governed by the concentration of the hydroxide ion, which is going to be governed by the leftover hydroxide ion that is unused after we blow beyond that equivalence point and keep adding base. So our pH would be calculated from the POH, which we can get from the hydroxide ion concentration. So you have to keep in mind what region of the titration plot you're in when you calculate the pH. When we first begin, we haven't added any potassium hydroxide. And so we're going to have to calculate the pH from an equilibrium of the dissociation of the HF in water. So this will be just the pH is calculated by the dissociation of the HF. In this region, we're going to have a buffer, and the pH will be calculated by the concentration of the buffer, and we can use the Henderson-Hasselbalch equation. All right, and so once we add, so we're starting with 150 milliliters of 0.1 molar HF. So if we add 150 milliliters of KOH, but our KOH is only half that concentration, then we're going to be at some point called the half equivalence point. We're still in the buffer region, and we'll look at what happens. We'll examine what happens in that region a little bit more thoroughly as we do that calculation. But we can still use the Henderson-Hasselbalch equation here. All right, and then once we add 300 milliliters of KOH, we should be at the equivalence point. All right, we should be at the equivalence point. And then we can go ahead and do an E calculation. Let's go ahead and just do that. We can go ahead and add 450 milliliters of KOH. And at that point, we're going to be in the hydroxide or basic range, right? And we'll calculate the pH from the POH. All right, so let's go ahead and get started and look at what these calculations will look like. So this is going to be a very in-depth study of a titration problem. All right, so let's first look at A when we have 0 moles or 0 milliliters of KOH. Okay, so in this region, this is the initial region of our graph right here. Before we add any KOH, the pH is controlled by the dissociation of HF. Okay, so HF plus water goes to H3O plus F minus. Okay, and so we can go ahead and draw an ice table. So we have initial, change, and equilibrium. So for just dissociation problems, we could just use an ice table. And remember, in our ice table, we start with concentration, not moles. So we have 0.10 molar HF, okay, and 0 of hydronium and 0 of fluoride when we first begin. Okay, we're losing X of the HF, gaining X of the hydronium, and gaining X of the fluoride. We don't know exactly how much that is, but it's going to be controlled by our Ka for HF. So at equilibrium, we're going to have 0.10 minus X. We're going to have X and X. Okay. So let's go ahead and set up our equilibrium expression. Our K is equal to X times X over 0.10 minus X, right? So that's going to be equal to X squared times 0.10 minus X. Now, if we assume X is small, which we can make that assumption here, we generally do, then we can set our, forgot to put the K in here. So let's go ahead and rewrite it. Our K, let's just put our K in, 6.6 times 10 to minus 4th is equal to X squared over 0.10. So X is equal to the square root of 6.6 times 10 to the minus 4th times 0.10. Okay, so that's equal to 8.12 times 10 to the minus 3rd. So looking back at our equilibrium expression, X represents our hydronium ion concentration. So the pH, so we could say that's equal to H3O plus. So the pH is equal to the negative log of H3O plus, which is equal to the negative log of 8.12 times 10 to the minus 3rd, which is equal to 2.09. So our initial pH, when we're just getting started here on this graph, is 2.09 before we add any potassium hydroxide. So B says, let's calculate the pH after we added 35 milliliters of potassium hydroxide, and that's 0.05 molar potassium hydroxide. Okay, so when we do these calculations, we always go back to the original amount that we started with. So let's go ahead and calculate for B. Okay, so we started with 150 milliliters of 0.10 molar HF. Okay, and we're going to add 35 milliliters of 0.05 molar KOH. So we need to do a before addition, and after addition problem. So we need to calculate the number of moles of each of these species before we get started and find out how many moles reacted. Okay, so let's go ahead and do that. I've got 0.150 liters of HF solution, and I've got 0.10 moles per liter, and that's equal to 0.015 moles of HF. Okay, let's calculate the moles of KOH. 0.035 liters of KOH times 0.050 moles per liter equals 1.75 times 10 to the minus 3rd moles of KOH. And we could just say that's equal to 0.00175. Might be a little easier to write. So let's go ahead and draw an equilibrium problem, or a before addition, and after addition table. HF plus KOH goes to what? KF plus water. Okay, so this is our reaction. Now we're actually adding our base and we're getting a reaction. So before the addition, we have a line. Our addition, we have a line, and our after addition, we have another line. And we need to calculate our amounts at each point. So we're starting with this many moles. So this before addition and after addition table, we use moles, okay? We use moles, not molarity. All right, so we've got 0 of this and 0 of this when we're starting. We're not concerned about the water because it's a liquid. 0.00175 is the amount that we're losing of our HF because it's reacting with 0.00175 of our KOH. Okay, so we're adding 0.00175 of the KOH. So for every 1 mole of KOH we add, we have to take away a mole of the HF. Okay, so we're going to end up with 0.01325 moles of HF, none of the KOH, but for every mole of HF that reacts with KOH, we get 1 mole of KF. So we end up with 0.00175 moles of KF. Now, we can go ahead and set up a Henderson-Hasselbalch equation. Remember, the Henderson-Hasselbalch is pH is equal to the pKa plus the log of the concentration of A minus over HA. Now, you might think I can't just plug moles directly in here, but remember the volume is the same on these. So if I put moles per liter divided by moles per liter, right, then liter is going to cancel. The moles are different, but the volumes are the same. So the only thing that's going into this equation is the ratio of moles. So we can just put the moles directly in here. We don't actually have to calculate the molarity, even though technically that's what this equation is asking for. So the pH is equal to the negative log of the Ka, right, plus the log of A minus. I'm going to go ahead and erase this up here because it's in the way, over HA. All right, and so the pH is equal to the negative log of the Ka. So let's go ahead and put that in. Negative log of 6.6 times 10 to the minus 4th plus the log of 0.00175 over 0.01325. So we can just put the ratio of moles in. Here's our A minus and here's our HA, okay, from our chart, because the volumes would cancel. So the pH is equal to 3.18 plus the log of 0.132, okay? So pH is equal to 3.18 plus negative 0.879, which is equal to 2.30. So our pH after 35 milliliters of KOH is 2.30. So if we go back up to our chart here, when we've added 35 milliliters, 2.30, we've actually increased our pH just a little bit, So C asked us to calculate after 150 milliliters of KOH. So after 150 milliliters KOH, let's go ahead and calculate our pH, okay? So initially we calculated earlier that we started with 0.015 moles of HF, okay? So we had 75 50 milliliters of KOH. Why did I have 75? I'm sorry. So I'm going with 0.150 milliliters of KOH, and I've got 0.050 moles per liter KOH, and that gives me 0.0075 moles. Okay. So let's do our table. Let's go ahead and write our equation. HF plus KOH goes to KF plus H2O. All right, now we're doing a reaction. Okay, so we get a before, our addition, and our after addition. So this is not really an equilibrium. This is our reaction. So that's why we're doing a before addition and after addition. And it's our moles that are reacting. So we need to calculate the number of moles we have. So we're starting with 0.015 moles of HF, which we calculated earlier, and we're adding 0.0075 moles of KOH. So notice that we're subtracting 0.0075 moles from the HF because it's a 1-to-1 ratio. So we're going to end up with 0.0075 moles of HF, okay? And we're going to have 0.0075 moles of KF after the reaction. So we end up with equal amounts of each. So let's go ahead and calculate our pH. So the pH is equal to the pKa, which we calculated earlier. That's the negative log of the Ka, plus the log of the concentration of A minus over HA. So we learned that we can actually just plug the moles in here instead of having to recalculate our concentration. So that's equal to 3.18 plus the log of 0.0075 divided by 0.0075. So the pH is equal to 3.18, okay? Because the log of 0.0075 divided by 0.0075 is what? It's 1. And the log of 1 is 0. So at the point where you have equal moles of acid and its conjugate base, the pH is equal to the pKa. So where you have equal moles of acid and conjugate base, the pH is equal to the pKa. And this is called the equivalent, or half the equivalence point. So this is called the half equivalence point. Okay, so our half equivalence point, and you could actually calculate your half equivalence point. It would be half the volume that it would take to get to the equivalence point. And you could actually calculate that. So our pH there is 3.18 at the half equivalence point. That's the half of the volume of our base that it takes to get to the equivalence point. All right, so next let's do D. After the addition of 300 milliliters of KOH. So we're initially starting out with 0.015 moles of HF, right? All right, and now we're adding 0.3 liters of KOH, and that is 0.050 moles per liter. So that's 0.015 moles of, that's here, 0.015 moles of KOH, okay? So now we're going to do our reaction. HF plus KOH goes to KF plus H2O, okay? And now we need a before, an addition, and after addition problem. So we need to calculate how much we have left after our addition. Okay, so we're starting with 0.015 moles of HF, and here we have moles. We're taking away, or we're adding 0.015 moles of KOH. So that means that because they react in a 1-to-1 ratio, this is a strong base. It's going to completely deprotonate the HF. So we're going to lose 0.015 moles of the HF. So we end up with 0 of this. All of our KOH reacts, so we got 0 of this. We end up with 0.015 moles of our fluoride. All right, and so that is actually our weak base. So we're governed by a weak base. All right, we're not governed by the Henderson-Hasselbalch equation anymore. So now we need to create an ice table for our dissociation of a weak base. So let's look at what that looks like. So now we've got KF. That's the only thing in solution, and it's going to be dissociating in water to give us F minus plus what? Plus OH minus, basically. All right. And so it's going to be reacting with water to give us the fluoride plus the hydroxide, because the KF actually, it will form actually HF. I probably should write HF. So it's the fluoride is reacting with water. I'm sorry, I got that wrong. The fluoride is reacting with water to give us HF plus hydroxide. I'm sorry. So now we can draw an ice table here. Okay, now we can draw an ice table where we're going to put in the concentration of, so remember, ice tables are concentration. We're going to put in the new concentration of our fluoride, and we're going to be starting with 0 of the HF and 0 of the hydroxide. Okay? So let's calculate the new concentration of fluoride. So we have 0.015 moles of KF. Okay, and we're going to divide that by everything we added in the volume. So 0.300 liters plus 0.150 liters. So this is our acid plus our base that we added, and we get 0.033 molar KF. Okay, so we got 0.033 molar fluoride when we're starting. We're losing X of that, gaining X of that, gaining X of that because we're making an equilibrium table. So we end up with 0.033 minus X plus X and plus X. All right, and so now we can set up our expression, but we need to do one thing first. We need to remember that KW equals KA times KB. And we can look up the KA for this acid. Remember, the KA is equal to 6.6 times 10 to the minus 4th, and the KW is 1.0 times 10 to the minus 14. So we need to calculate our KB because we can't use the Ka here because this is basically dissociation of, or the dissociation of a base. Okay, so dissociation of water by a base. So we need to use the Kb here, and the Kb is equal to the Kw over the Ka, which is equal to 1 times 10 to the minus 14th divided by 6.6 times 10 to the minus 4th, and that's equal to 1.5152 times 10 to the minus 11th. So now we can set up our equilibrium expression. So we're not talking about dissociation of an acid, we're talking about dissociation of water by a base, and therefore we need to write the equilibrium expression with the Kb. So let's just go ahead and write that down. Kb is equal to fluoride. Oh no, I'm doing that wrong thing again. HF times OH minus divided by KF. All right, so that's going to be equal to X times X divided by 0.033 minus X. Now, if we assume X is small, we can make that assumption. That'll help us to solve our problem. So let's go ahead and write everything in. 1.5152 times 10 to the minus 11 is equal to X squared over 0.33. So X is equal to the square root of 1.5152 times 10 to the minus 11 times 0.33, which is equal to 2.236 times 10 to the minus 6, and that's our hydroxide ion concentration. So how does our hydroxide ion concentration help us find our pH? Our pH is equal to 14 minus the pOH, remember, because the pOH plus the pH is equal to 14. So that's equal to 14 minus the negative log of the hydroxide ion concentration, which is 2.236 times 10 to the minus 6. Okay, so the pOH is the negative log of the hydroxide ion concentration. So the pH is 14 minus the negative log of the hydroxide ion concentration. Okay, so gotta plug my battery in here, guys. Okay, I gotta plug my battery in. There we go. All right. So the pH is equal to 8.34. And that's what we would expect. We would expect our pH to be a little above 7 because this is governed by the dissociation of water by a base. Okay. And so we had 8.34. Okay. Now we're going to do our last calculation, and that is the pH when we're governed by just the excess hydroxide ion concentration. And so after adding 450 milliliters of potassium hydroxide. So let's go ahead and calculate that. So initially, we always go back to the beginning amount of acid. So 0.015 moles of HF, okay? And so we've got our, let's go ahead and write our problem. Well, let's go ahead and calculate the moles of KOH. So we've got 0.450. I am going to run out of room here. Maybe we won't run out of room. 0.450 liters of KOH times 0.050 moles per liter, and that gives me 0.0225 moles of KOH, okay? So HF plus KOH reacts to give KF plus H2O, okay? So before addition, and after addition, okay? Water's a liquid, so we don't care about it. We're starting with 0.015 moles of HF. We're losing all of that because we're going to be adding 0.0225 moles of KOH. And so we're left with no HF, but we subtract the amount of KOH we lost and we get 0.0075 moles of KOH. So we lost the 0.015 moles of KOH, so we had to subtract 0.015 from that, and we end up with 0.0075 moles of KOH, and we get 0.015 moles of KF, okay? All right, so at this point, our pH is governed by the concentration of the hydroxide ion concentration. Okay, and the hydroxide ion concentration is going to be 0.0075 moles of hydroxide there, divided by our new volume, which is 0.450 liters plus 0.150 liters, and that's equal to 0.0125 molar hydroxide. Okay, so since the hydroxide is a strong base, that's going to have a stronger effect on the pH than the fluoride, and therefore it's going to govern the pH. Okay, so the pH is equal to the negative log of the hydroxide ion concentration, which is 0.0125, okay, which is 1.90. Okay, that's the pOH. The pOH is the negative log of the hydroxide ion concentration, which is 1.90, and the pH is equal to 14 minus the pOH is equal to 14 minus 1.90, which is equal to 12.10, okay? All right. And so if we remember the hydroxide ion concentration from the fluoride, so let's think about why we didn't need to count the fluoride. The hydroxide ion concentration from the fluoride at the equivalence point was 2.236 times 10 to the minus 6. And that was much, much less than the molarity of the hydroxide ion due to the potassium hydroxide excess here. And that's why we don't need to consider the small amount of hydroxide from the fluoride. Okay. So let's look at the 12.10 on our chart. Okay, so let's go back up to our chart. And so our graph of our titration. And so the pH, this is really a not to scale graph, right? So the pH here is going to be equal to 12. And so we've blown past the equivalence point and we've graphed a titration of potassium hydroxide of hydrofluoric acid, a weak acid with potassium hydroxide. All right, so thanks for watching.